Okay, so welcome everyone. So today it's our pleasure to have Jianyu Hu, who will be talking about a global structure preserving kernel method for the learning of Poisson system. Thank you.
Okay. Hello, everyone, and thanks for the introduction, and thanks for the invitation by Professor Lin. It is a great honor to share my recent work at this machine learning and dynamic system seminar. So today I will present the global structure preserving kernel method for the learning of Poisson systems. This work builds on our previous research on learning Hamiltonian systems in Euclidean spaces, extending the framework to Poisson structures and the manifold setting. Okay, this work is joined with Juan Pablo and Dain. So I will outline the method in the following sections. So at first, for the context and the objective. So as we know, Hamiltonian systems are essential tool for modeling physical phenomena. They are typically described as the Hamiltonian equations in 1.1. So here XH is the Hamiltonian vector field associated with a Hamiltonian function. J is the canonical symplectic matrix. However, in general, the phase space of a Hamiltonian system is not a flat Euclidean space. It is often a symplectic manifold or a Poisson manifold. This motivates us to go beyond simple mechanical systems. So in this talk, I will focus on the learning on general symplectic and Poisson manifolds. On a symplectic manifold, the Hamiltonian systems can be defined via a symplectic form. And on a Poisson manifold, the Hamiltonian system can be defined via a Poisson bracket. In fact, the Poisson systems are more general, as for any symplectic form on a symplectic manifold can induce a Poisson bracket. Yes. Another important example of Poisson system is the Poisson mechanics. An important difference between symplectic and Poisson manifold is that the Poisson tensor could be degenerate. It implies that the Poisson algebra has a center which contains non-constant functions. These functions are called Casimirs. So as a result, Hamiltonian functions are defined up to Casimirs. Okay, now for the objective. So in our setting, suppose we are giving random samples of the noisy Hamiltonian vector fields. So here capital N is the sample size. XH is the Hamiltonian vector field on a Poisson manifold. These epsilon are observation noise. So the goal is to recover the Hamiltonian function from this observation data in a structure preserving way using a RKHS. So this learning task is on the general Poisson case. And I will formulate a global solution to this problem, to this learning problem. So here the global means that our learning approach doesn't depend on the choice of double local coordinates. To make the problem explicit, we consider the following optimization problem. That is, we search the optimal function within the entire RKHS with respect to the empiric risk functional. So here, lambda is called the regularization term. And we also consider its statistical version. I should point out that these two risk functionals are not always well defined, because here we take the Hamiltonian vector field over the functions in the RK-trace. Moreover, because due to the degeneracy of Poisson tensor, this learning problem could be ill-posed in general. So here, the regularization term is necessary. So as we will see later, this regularization term plays an essential role in ensuring the uniqueness of the solution to the minimization problems. Okay. So the goal in this talk is to establish the well-posed of the optimization problems and to derive the convergence rate and the error bounds. The idea is to formulate a global differential reproducing property on Riemann manifold, and then to obtain a global form of the solutions via a generalized differential grammar metric. We will see it later. And finally, to derive the convergence rate via the operator representations. At first, I introduce high-order differentials and the space CBS on the general Riemann manifold. So if a function f is in CK class, the k-order differential of this function f can be defined in this inductive way. And the norm of the CBS space is defined as the summation of the uniform boundaries of all differentials with order equal or less than s. Okay, now I can present the following differential reproducing property on Riemann manifold. So in this theory, if the kernel lies in the CB 2s plus 1, then for any k from 1 to s, the k-order differential of the kernel at the point y along the vector still lies in the RK-trace. So this is a function with respect to the second variable of the kernel. So this function lies in the RK-trace. Moreover, a differential reproducing property holds, as shown in 2.5. It means that the differential of any function in the RK-trace can be expressed by the RK-trace paralleling between the differential of the kernel and the function itself. As a result, we can embed the RK-trace to the CBS space. So in a summary, it means that if we have the regularity of the kernel, then we have the corresponding differential reproducing property and the corresponding embedding. This series is very important, not only to guarantee the well-posedness of the minimization problems, but also to provide an operator framework to represent the minimizers. Okay, but before introducing the operator framework, we first rewrite the Hamiltonian vector field using the compatible structure. The compatible structure is a vector bundle map from the tangent bundle of the Poisson manifold to itself, defined through the Poisson tensor and the Riemann matrix. So here the B sharp is a bundle map induced by the Poisson tensor. G flat is the bundle isomorphism associated with the Riemann metric. So using this compatible structure J, we can rewrite the Hamiltonian vector field as the composition of the compatible structure and the Riemann gradient operator. Notice that here we are not imposing Kernel manifold despite the notation. In the case of symplectic spaces, this compatible structure J is the canonical symplectic matrix. Okay, now I introduce the operator framework. So in this talk, I will always suppose that this compatible structure J satisfies these boundary conditions. And this assumption is very mild. For example, in Euclidean space, this inequality always holds, as we can choose the function gamma as the constant function 1. As we will see later, the boundaries of J gives us the boundaries of the operators A and An. Okay. The operator A is defined as a map from the RHS to its associated Hamiltonian vector fields. We can show that if the kernel lies in CB3, then the operator A is bounded linear from the RHS to L2 space. So using this framework, we can compute its adjoint operator A star and then compute the operator Q. It can be shown that this operator Q is positive in the trace class. Okay. And similarly, we can obtain the same properties of the operator An, which can be regarded as an empiric version of the operator A, and also operate the property of Qn. So now we are ready to answer the first question. So if the kernel K belongs to CB3, then the minimization problems admit unique solutions which can be which have this operator representations. However, in practice, these representations are not convenient to compute the estimator. So to get the kernel representation, we first define a generalized differential grammar metric mapping from this product tangent space to itself. So here I briefly explain the notation here. So K is the kernel. So we can take the Hamiltonian vector field with respect to the first variable of the kernel at these sample points. Then after pairing with a vector C in the product tangent space, this can be regarded as a function with respect to the second variable of the kernel K. Then we can take again the Hamiltonian vector field to that variable and obtain a vector in this product tangent space. Okay. In even dimensional Euclidean spaces, this generalized differential grammar matrix reduced to the standard one. There is an important property for this generalized differential grammar matrix. It shows that if the kernel belongs to CB3, then the grammar metric is symmetric and positive semi-definite. Okay, then we are able to obtain the differential representative theory on Poisson manifold. So in this theory, we obtain an exact form of the solution to the minimization problem. Moreover, this solution is global on general Poisson manifolds. An important difference to the standard representative theory is that the differentials are involved in this expression. So here we take the Hamiltonian vector field of the kernel K here. So this can be regarded as a function of the second variable of the kernel. Yeah. So here, since Gn is positive semi-definite as shown before, so C hat, the coefficient C hat is well defined and actually is unique. Okay. Then we can compute the estimator globally using the data and the given kernel. So one may wondering why the estimator is unique, not up to Casimir functions. The reason is in the use of regularization term. In fact, we can show that the estimator lies in the orthogonal complement of the line space, which is defined as this. Specifically, it can be shown that the estimator plus any Casimir function is a minimizer if and only if this Casimir is 0. So this means that the estimator is the unique minimizer of the minimization problem. Okay. Now we turn to the convergence analysis. We obtained the error bound through our previous operator theoretical representation. And in fact, we can decompose the total reconstruction error into two parts, the estimation error and the approximation error. The estimation error can be further decomposed into the noise part and the noise-free part. And we can use these techniques to analyze each part. Okay, the first result is the peg bound with fixed regularization parameter. So this fixed means that the parameter lambda is independent to the sample size. Okay, so if the kernel is in the CB3 and the ground truth satisfy this source condition 3.1, then with probability close to 1, the total error is arbitrarily small as the sample size is large enough. Okay, this is the peg bound. However, this result doesn't provide any convergence rate. So to address this, we consider a dynamical regularization parameter. So in this case, the regularization parameter is dependent on the sample size with the parameter alpha. Okay, and under the same conditions, we obtain that for any alpha belongs to the interval 0, 1 over 3, the total error will tends to 0 as the sample size tends to infinity. And the convergence order is the minimum of these two constants. Okay, this is, and if we further assume a so-called coercivity condition, then we can improve the convergence rate of the parameter for alpha from 1 over 3 to 1 over 2. Yeah. And also improve the convergence rate here. Okay, these are the error bounds and the peg bounds of the theoretic part. Yeah. Now I present two examples to illustrate our result. The first example is the rigid body dynamics. Picture A, picture A is the ground truth. Picture B is a learned Hamiltonian, and the picture C is the learned Hamiltonian adjusted by a Casimir function. So we observe that the error of the Hamiltonian vector field is very small. Okay, and another example is a Hamiltonian defined on a manifold S2 times S2. Okay, and we can draw the global head map. So the left one is the ground truth, and the right one is the learned. The result demonstrates that the learning performance is pretty good. Yeah. Okay. Oh, and finally, I want to present the error bound with respect to the sample size. So the picture figure A shows the RKHS norm error as a function of the sample size. So if we take the log map, take the log picture with the same data, we can the picture will like in figure B. So in the right picture, we can see that we can see clearly the convergence rate. Yeah. Okay. So I want to end this talk with the summary and further works. So in this talk, I present a global structure preserving kernel method to learn Hamiltonian system on symplectic and Poisson manifolds. And then this framework provides a global exact form of the minimizer, along with the error bound and the convergence rates. So in the future, the following directions may be exciting to explore. So the first is to learn stochastic Hamiltonian mechanics. For example, in Bismuth formulas. And also, we can study to preserve other geometric structures such as momentum map, contact geometry, and so on. And also, we can apply this method to quantum mechanics and statistic mechanics. Okay. I think that's all. Thanks for your attention. Yeah.
Thank you very much for the nice talk. Any questions or comments? Yeah, maybe I have a few questions about the reproducing property that you mentioned on manifolds.
Yes.
So like in general, we don't know. I mean, we don't know what manifold we are in, right? So so if you perturb the manifold, will the results be perturbed, or do you have sort of robustness with respect to this reproducing property? I mean, it seems like a nice property. I'm just like wondering how robust it is if we assume that we don't know the manifold, and then we try to learn the manifold from data. How sensitive will your results be? It's not this one. It's I think it was one of the.
Yes.
It was in the previous slide, like a reproducing property on manifolds.
Yes. Okay. I guess it's here. Yeah, this one.
Yeah, this one, 2.5 exactly. Yeah.
Yes. So actually, this properties works for general Riemann manifolds. General Riemann manifold. Yeah. So it is a so it means that if you want to so if you if you have the regularity of the kernel on this manifold, on the product space of this manifold, then the corresponding architraves of this associated with this kernel will the functions in this space, the corresponding in this space will have these three less properties. Yeah.
Yeah, so
In our learning problem, we want to learn a function on a Poisson manifold. Yes, the Poisson manifold is actually given. We just observed the random Hamiltonian vector field of a function on that manifold. So
yeah, so my question is, assume that you don't even know what the manifold is, right?
yes, that's a good question. But
Yeah.
here, I think we should know the Poisson structure of the manifold. So our learning method is in the knowledge of the Poisson structure.
But this
So,
but yes, I think you are going so I'm just asking a simple question. We are thinking for a more complicated problem. I'm thinking about like property 2.5, right?
yes.
Do you require any knowledge about the manifold, or is it like general, independent of the manifold? It's just like I'm just talking about the reproducing property.
Actually, this is a general property for the Riemann manifolds. Yeah.
Yeah, but you don't use any information about the manifold in it, right?
Sure.
Do you or you don't?
As here you have a Riemann metric, yes, because you want to take the dual of the vectors in the cotangent boundaries, cotangent vector space and tangent vector space. Yes.
Yeah,
Tangent space.
so this why I think this is why I'm asking you. So if you don't know how to if your estimate if you don't know M and then you estimate M from data, like estimating manifold from data, so this property will be affected, isn't it? Will it be affected or not?
I think you need to load the Riemann metric of the manifold. Yeah.
Okay, yeah, that was my question. Yeah, I was just trying. So you need to now yeah, okay. So it's sensitive in a way to the knowledge of the.
But this property holds for any Riemann metric for any complete Riemann metric of this Riemann manifold. Yeah. So you just giving a Riemann metric, then you have this formula, and you change another Riemann metric, you also have this formula. Yeah.
Okay. Yeah, I see. Yeah, and I think Tom, who's here, he also worked on learning manifolds from data, isn't it? Tom, you want to ask a question?
I was actually kind of interested in a similar idea. I mean, that I came in late, so I don't know. I may have some naive questions, but like for example, if you had a robotics problem like linked rigid bodies, and so you have it expressed in some you record your data in some inconvenient form, like just the centers of masses moving over time, which has no kinematic constraints. They're implied, but you don't know them, and maybe it's Hamiltonian, but only in some other generalized coordinate system, which you don't know. Like, can you learn that mapping? As this is part of some kernel method.
You mean for rigid body problem? So what do you observe?
But so like linked rigid bodies. So like the limbs of a robot, for example, right? They're Hamiltonian, but they're maybe say you observed only the positions of the positions and velocities of these linked bodies, but there's kinematic constraints that you don't know about.
And that's a good question, but in this setting, currently, as I say no, because in our settings we are actually assume a full assumption of the observation data. So these are the noisy Hamiltonian vector field our data.
It's in that form.
Yes, and actually here we cannot do the constraint. Yeah, no, yeah.
And I suppose your pack bounds rely on the learning part only being about the vector field, not about some transformation also.
Sure. Yeah.
Thank you.
Thanks for the question.
Yeah, thank you. Yes. Any other questions or comments? Yeah, all right. Seems okay. Thanks again for the very nice talk. So it seems that there is a lot of good work to be done afterward. Yeah.
Yeah, and thanks all the audience. Yeah.
Yeah. Thank you very much. Yeah.
Bye.
Yeah,
Bye. Bye.
Bye.